So this is the problem we're going to look at today. Let me put that here. Okay. I'll give you a couple minutes to read this. So just imagine you have a large building, and you have a start point and an end point, and you have to make your job is to kind of make your way from the start point to the end point, or for anybody. And there are doors between different rooms. Right? And each door has allowable badges. So each of these doors has allowable badges, which is given as a range for min D, max D. So if the door is D, you get these two numbers. So if somebody has a badge number that's between those two numbers, they can pass through the door. And there are so you have N rooms, M doors, and K people or badges, same thing. K people, and each one has a badge. So you're told that N is at most 1,000. Number of doors is 5,000. And the number of badges can be as big as 10 to the 9. So you sort of know what to watch out for.
Yeah.
Right? So you should quickly pay attention to that, and then you can worry about it later. And you're asked to figure out how many different badges can go from the start to the destination. And you look at all the badges, numbered 1 through K. You can read all this other stuff, but it pretty much tells you the same thing. It says things about the doors and the rooms and the people and the badges. Then it says that you're told what the start room and the destination room are. And then it says that for each of the doors, you're given a min and a max. And the door goes from room A to room B. So it tells you it goes from this room to this room. And that's it.
So my first thought is, at least you see it, I would convert it to a graph.
Convert it to a graph. Very good. Yeah?
Oh, wait, I think they said, and non-graph, so this is directed graph? So you go from room A to room B?
Let's see. Do they? Where do you see that?
The last paragraph in input.
Yeah, and not back. Okay, yeah. Cool. So when you enter a door, you kind of flash your badge and it checks the range, and if you're in the right range, it lets you in.
Okay.
So graph sounds like a good start. So your thought is model the rooms and doors as a graph, as a directed graph.
Yeah.
Okay, good. Then what?
For every node you have, so the start node, which we give you there.
So you got a start node, you got an end node.
At the start node, you have all sets of badges, and then for each and every single edge you take.
So let's try a simple solution that we know will work, and then worry about improving it. What's a simple solution?
And just go through all the doors and see which one.
All the doors.
Yeah.
For what?
For every room, go through all the doors and see which door.
But what is it that you want as output?
Oh, the max amount of badges will start at.
Right.
Is it not go through a door and see which door decreases?
For whom?
Huh?
For who?
For the number of badges. For the people with badges.
Right, but each person has a different badge.
Can you not try every door in a room?
But I don't even know if I can get there. So I've drawn a graph. Here's my graph. This is the start and this is the destination. So each vertex is a door, right? So actually that's not quite the way, no, sorry, each edge is a door. So there's a door here, 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 right? Okay. So yeah, I can try every door, but how does that help me? In fact, let's say that I mess you up and um,
Yes, you can never reach the destination.
right. So uh, so in this case, I can never reach the destination, but it could be that uh, so what do I do now? Do I still have to check every door? How does that help me?
Oh, so check every door that leads you to destination, or every path.
But I don't know what leads to the destination. How do I figure that out?
So you're not find path using GFS?
Find a path, is that good enough?
No, you want to find all the paths, right?
Right, so how, but finding all paths is crazy.
Yeah.
There may be too many paths. So what do I do? All right, so let's try and make our, so even if you do that, then what? Let's say I find all paths, then what?
You want to try every single path.
Sorry?
You want to try every single path
For what? For whom?
for all the badges, no? Every
Right,
time you go through
so,
it,
so I want to hear that. Am I going to take one badge at a time? What is your algorithm?
oh, okay. No, would you not take all the badges and every time you go through an edge, you would cut down on the badges that didn't?
But different badges could take different paths. It's not just one path. I don't care how these people get there. I want to know how many people in my organization are able to go from start to end.
Oh, wait a minute. Instead of, so that's a large amount of badges, right? What about
Uh-huh.
you choose the path that has the lowest min and then the highest max?
All right, so before we go there, let me go back to what I said earlier. Give me a clean solution that works. Doesn't matter what the how inefficient it is.
Okay, I think this was.
Yeah.
So let's say you know all the paths from start to destination, right?
Okay, this all paths idea is quite crazy. You know that already. Yeah. I can't find all paths because typically there are too many of those. So that is too many. The number of badges is too many. So it's not okay. So I did say forget about efficiency, but still there is a limit to how inefficient. So you're first of all, I don't know an algorithm that will find me all paths. That just doesn't exist. Well, I could write every possible combination and see if that's a path. And for each of those paths, I can go and try every possible badge, keep track of this, blah, blah, blah. That's crazy. Right? You can see that it's just not going to work out. Okay, so we do have a solution that works. We're going to try every possible permutation that could be a path and try every possible badge on each of those paths.
But, okay, so instead of finding every single badge,
Yeah.
so that's 10 to the 9, that's pretty large.
Yeah.
How about we just keep track of the bounds?
Okay, but you didn't really solve the problem with all paths because I can't even do all paths.
Yeah.
So you have two challenges now. One is the number of badges is too many, and the other is finding all the paths doesn't seem all that feasible. All right, so your idea for the badges is to work with ranges somehow. Okay, what exactly is that idea? Tell me more.
So you want to find the path from start to destination that has the widest range, but then that should include the most amount of badges.
Uh-huh. But that'll tell me for a single door. Now what do I do? So, yeah, when I got in here, I have only one door, so that tells me what range of people can get in here. But now I have three different possibilities. So what do I do?
You go through each door, then
You label it with a range.
yeah, and then you do.
Now how do I know that I can't go blah 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 around and improve my range? What if I shouldn't have gone in here, I should have done something else and then come back and gone through this door? No, that doesn't make sense. Okay, so for each door, you're keeping track of the range, but then the range is the same as whatever the door allows. So why should it be any worse?
Okay, I think this is something I'm missing. Let's say we go through the first door, right?
Yeah.
Let's say the range that first door was like 510.
Okay, fine.
Let's say now we have a second door, which is
This or this or this?
yeah, sure. Let's say the second one.
Is that one?
Yeah.
Yeah.
Let's say that range is 7 and 10.
Yeah.
So now the lower bound will be the maximum of.
Okay, so you're going to take intersection of the ranges.
Yes.
Okay, got it. Yeah. So then you're going to label this door with the intersection of ranges, and then yeah. But now let's look at something a little harder. So let's say you're here. There are two different ways to get in here,
Yes.
and one way to get out. So what am I going to do? I'm going to take the range of this and the range of this and take the intersection there.
Okay, so for that current door,
Yeah.
for that current room, for the doors that go into it,
Yeah.
that room should have
Should have a range.
yeah, should have a range, but that range should be the maximum between those two doors coming in, whichever has the wider range.
Yeah. Okay.
Then for the door coming out,
All right.
yeah.
So this range idea looks like it might work out. Okay.
Oh, what about for the ones? How many rooms are there? 1, 2, 3. Do we only have to go over the number of rooms? And for the rooms that don't reach the destination, we put a really small range. To show that it wouldn't work at all. And then we only have to look at the room at destination B.
Something like so. No, the badge, the range idea should work out. It looks reasonable to me, but I still don't see the other pieces. I don't see how the paths are going to work out.
Yeah, so instead of now finding all the paths,
Yeah.
we only need to compute the range for all the rooms.
Uh-huh.
Once we do that,
Yeah.
we can just look at the destination room and see what that range is. Because that should be the largest range, taking into account all the other rooms.
Smallest range, you mean?
Smallest range? Oh yes, the smallest range, yes. Because you're taking maximum range, yeah, okay.
Now, for you're thinking of a range always as a minimum and a maximum. In reality, it can be in two different pieces. So it's possible that if I look at this room, maybe 3 to 5 can come through this door, and 7 through 9 can come through this door, and maybe both are allowed here, or maybe part of one and part of the other is allowed here. So now the ranges could get split into as many pieces as you want. So what I would suggest for you, the range idea is a good idea. Keep that in your head, but you haven't really solved the graph problem. What do I do with the graph that I built? Because I need to know what graph algorithm I want to use. Otherwise, it's kind of very hard for me to do anything with this, right? So you know the graph algorithms. We've got depth first search, breadth first search. We've got minimum spanning trees. We've got shortest path. And we've got all pair shortest path. And then we have other fancy ones like network flow, blah, blah, blah. Let's forget about those. Hopefully this is easier. Which one am I using here? And why? And how? What do I do with that? When I have a source and a destination, what algorithm do I use? Is this a weighted graph? Is this a directed graph? These are the questions you have to ask.
Is it weighted? Can the range represent the weight of the edge?
Weight typically has to do with distance
Okay.
or a cost. Don't see that here. So it's not a weighted graph, it's a directed graph. So in order to figure out whether I can
So BFS could find from starting at S, we could reach D, but that will give us one path, and that might be suboptimal.
right.
So we might not want.
So you're saying breadth first search or depth first search can only find one path?
No, we can let it run, and then it'll find it.
Uh-huh. Okay, so really the question is about reachability, and then within reachability there are these constraints with the badges. If I want to do reachability, that's the same as connectivity, right? So in order to check whether D is reachable from S, even breadth first search and depth first search should work. Okay, it probably doesn't matter which version you use, but essentially as you do that, you have to also deal with the ranges of badges that you're allowed through the doors, right? So you have to combine these two things now. You could use Dijkstra's, but Dijkstra's algorithm is for weighted graphs. So we don't need this fancy stuff. For unweighted graph, Dijkstra's algorithm is essentially the same as breadth first search, right? Because breadth first search gets to one edge and then two edges and then three edges and so on. So let's just say I stick to simple breadth first search, right? I start from the source, I do breadth first search, figure out all the rooms I can reach, and then all the rooms I can reach from there, blah, blah, blah. And as I do this, I also keep track of the ranges. Would this work somehow? It might, right?
Yeah, it would still
Okay.
And then once we reach D, will we choose the best range?
No, look at what they want. My machine went to sleep. Yeah. What do we want?
How many people points per destination?
You want the number of different badges that can get from S to D.
The maximum, right? Or just a number?
Just the number.
Oh, just a number? Oh. Okay. So yeah, we can just find one path from S to D, and we can think of a number.
No, you're not getting it. You want to count all the people who can go through from start to destination.
Yeah, so why can't we not just find one path from S to D, get that range at D, and then count how many people fall within that range?
That's only one path. Who cares? There may be 49 other paths or 4 million other paths.
I see.
So go back to what we said here. We're combining what and what? We're combining the badge range with something else. What's that?
The room range?
Well, how are we going to solve the graph problem?
Oh, graph search.
Right. So these are the two pieces we want. So let's start with breadth first search. Let's worry about the range a little bit later. Now we don't want to use breadth first search to find a path. You got to get rid of that idea because that's going to get you into trouble. So you're doing breadth first search from here. First thing you do is to go to a neighbor. From the neighbor you get to all the other neighbors. From there you get to other neighbors. And there's only one there. From there you get to other neighbors, and then other neighbors, and then you finally hit the destination. And every time you go through an edge, that's a door. An edge is a door, and you refine the range. The problem is that you might simply get too many fragments of these ranges, and that's going to get you into trouble. Okay? So this is where you need a slightly different strategy, and that's what I'm going to tell you about. But is this solution clear to you? Yeah. So you start with the full range of 0 through 10 to the 9. Then at each place, you're going to refine the range, but the range of people that can enter this room can be crazy. You might have it in a million pieces. And that's where you're going to run into some trouble. Okay? Because there may be a million ways to get to a certain vertex, and so each one may have a different range, and each of those you have to keep track of. And that's too many.
To make sure to see if I'm in the right direction with it. So solving a smaller problem, since a solution to a smaller problem can lead to helping us solve a slightly bigger problem.
Yeah.
That means we need to use TP for this, right?
Yeah.
Okay.
Give me just a second. I need to respond to this. Sorry. All right, any thoughts?
Yeah, no, I don't think I have any good ones.
So part of the problem with doing it the way we just described it, the way we described it will work. We're doing breadth first search. Every time we come to an edge, we figure out how the range gets refined. The problem is that the range can be in many, many pieces, and the number of pieces could be proportional to the number of paths, and the number of paths can be very, very large. Okay? Each path could give you a different range, and they all are going to be, let's say, disjoint. If they are overlapping and so on, then it works out nicely. But if they are not, you're going to have to deal with each one of these ranges separately, and in the end, you have to go and count them. So that works. The only problem is that the work you do depends on something like 2 to the m, which is the number of possible paths. Sorry, 2 to the n actually, which can be very, very large. And I can set up the graph in such a way that that really happens. Okay. Now, what happens then is the whole thing then becomes 2 to the n times k, because you have to do this in the end. You have 2 to the n times m, which is the cost of breadth first search. Okay. So breadth first search is something like m plus n, and the badge range thing can be as big as 2 to the n. And this is going to be a problem for you. You just can't do this. So we are going to have to come up with a slightly different strategy. And for this, I'm going to take you back a couple of steps and ask you to think about how you can, if I gave you a badge, let's say that your badge number 49, and you are ready to see if you are able to walk through, can you come up with an algorithm that checks whether 49 can go through from S to D?
That's different from the one we just talked about?
This is different from the one, well, it may be the same, who knows, but let's see if we can answer this question. And how long does that take you? So now I have a specific badge, and I want to know if I'm able to get from start to destination. So I could essentially go and check every door, but that still doesn't help me because I still don't know whether I can get from source to destination. So what do I do?
Hey, what do you mean, if you check every single door, you don't know if you can reach the destination?
Yeah, I mean, okay, I checked all the doors. I know that I can get through this door. I can get through this door, this door, this door, this door. Now what? That still doesn't help me. It doesn't solve the problem. It doesn't tell me whether I can get 49 can get from here to here. So what is the algorithm?
Do you now only move to the next door if you're within the range of that?
What is next door? I don't know what next door is.
The neighbor?
Because at each time I may have 4 different doors. So I don't know what next door is.
It's the neighbor of the current node.
That's not good enough. So again, you're not thinking in terms of graphs and graph algorithms. Okay? Think in terms of these black box algorithms, and because they've all been solved for you. There's no point in you trying to start from scratch. Okay? So thinking in terms of where you are and what my next step is, that just doesn't help you. You need to think in terms of these graph algorithms. So now I have a graph, which I also drew over there. Some of these edges are, and now I've been given a certain badge number, so let's call this K. And if it helps you, you can think of K to be, say, 49 or whatever your favorite number is. Now I want to know if 49 can get from source to destination. The way I do this is I go through, let's say, I go through each of the doors and figure out whether this guy can make it or not. So let's say I say this is okay, this is okay, this is okay, this is okay, that's okay, and that's okay. So does this help me? So what I'll do is, I will throw away the edges that I cannot enter, or 49 cannot enter. And now what do? I'm going to run breadth first search, because I just need to know whether S is connected to D, whether there's a path from S to D in this remaining graph. So what this is telling me is that for a given value of K, I can do breadth first search and figure out whether this person can go from S to D after I do some initial screening saying which doors are okay. Some doors will be locked, other doors will be not. I can feed that into breadth first search and do this quite easily. So how much time did that take me? For a specific value of K, I can do breadth first search, starting from S, and check whether I'm able to reach D, and check if D is reached for this particular batch. So the time it takes for me is going to be breadth first search is m plus n, and since I'm doing this for every value of K, if I do this for every possible K, it's going to be this times K. And that's too much because this is 1,000, this is 10 to the 9. You're now talking about 1 trillion, you're in trouble. So this is not working out. So how do I now handle this? And what I'm going to show you is how to approach this. You know that there is a minimum and a maximum for every door. What if I take all those values? So here is my line. Here is 0, and here is 10 to the 9. And I take all the minimum and maximum values. So maybe one of the doors goes from here to here, the other goes from here to here, third one goes from here to here, fourth one goes from here to here, and so on and so forth. So here are all the minimum and maximum values. Now what should I do? Well, the nice thing is that all the numbers in this range have a nice property. And what's that? I don't care which one I test because they're all going to behave the same. Right? There is no door in the entire building where this guy is going to behave differently from this guy, because all the ranges are exactly the same for these two people. So therefore, I don't need to try each possible value of K. What do I have to check? For each range, I need to check one value. Right? For each interval here, I need to check one value. How many of these intervals are there?
The number of doors.
Exactly. And number of doors is m. That's the number of edges for our graph. So therefore, well, there are actually 2 for each door. So there are 2m values. So how many of these ranges? Well, it's 2m plus 1 or something like that, right? There's one over on this end and one over on that end. So let's just say 2m plus 1. Well, actually, I don't need 2m plus 1. I only need 2m minus 1 ranges. Because anything to the left of this guy, they're not relevant for us. Anything to the right of this, it's not relevant to us. They're never going to get through any of the doors. So I only have 2m minus 1 ranges because there are only 2m points here. What I'll do is I'll just pick an arbitrary number, or maybe the middle number in each range, and test them. And then for all the ones that pass through, I'll just add up the size of that range. because I don't have to test for each one. Should I repeat that?
Yeah, repeat the add up the size of each range for.
So let's say that this range has 100 numbers.
Uh-huh.
Let's say this range only has 50. This range has 200, and so on. All the ranges need not be equal, right? Because we don't know where the minimum and the maximum values are. You don't care which one is a minimum or which one is a maximum. They're just ranges for now. In each of these ranges, I know all the guys will have the exact same set of doors they can go through. I don't have to differentiate between them. I just have to check one of them. I'll check the middle guy, and if the answer is yes, I can get from source to destination, I'll just count 100, because all those 100 are going to behave exactly the same. Then I'll go to the second range, take the middle guy, do exactly the same thing, but with a new label now, and I know what to do for a certain label. Right? And that one, let's say, is 50. If the answer is yes, I'll add a 50 to the number of people that can go through. Right? So for each range, if that range is okay, if the range of numbers, if anybody in this range can reach from source to destination, I'll just add up the size of that range. I do this for each of the ranges. So how many different numbers do I test? That many. That's roughly 2 times 5,000, 10,000. Right? So for 10,000 different badge numbers, I'm going to run breadth first search. Okay? So now let's look at the time complexity one more time. I've got breadth first search, which is m plus n. And I don't have to test this for every value of k. Instead, I'm going to test this for 2m minus 1 values of k. And then I have to do some extra work where I add up the numbers. How big is that? Well, n is 1,000. This is 5,000. So let's just say 5,000 here. This is 10,000. So that's 10 to the 4th. This is 10 to the 3, something like that. So this looks very manageable. Is that clear?
Yeah.
Well, I have one more cost, and that is m log m, because I have to sort these numbers to find the ranges. So there's a m log m cost. M is again 5,000, so that's going to be some small number. So so what's my algorithm again? I take the minimum and maximum values of every room in the building. I sort them. I get ranges. For each of those ranges, I pick either the middle number or an arbitrary number there. I use that as a model label number, and I say, can this person get from source to destination? And if the answer is yes, then I add up the size of that range. Otherwise, I go to the next range. And at the end of this process, I would have a count of how many out of the billion people, billion badges, can actually go from source to destination.
That makes sense.
So here we are combining graph with some other trickery, right? So that's what this problem is about. Let me see how we are doing with time. Let me just show the slides so that people who are not in the room can quickly look at this. Okay, so your problem is, let me put this on. This problem is called the security badges problem, and it's on VJudge. You can find it. I just typed it. I don't know what happened to it. Yeah, so this is the problem for those of you who are logging in remotely. If you type security badges on VJudge, you can find this. And the problem says you're given a building with a bunch of rooms and doors, and for each door there's an allowable range of badges that can walk through that door in a certain direction. And you're asked, there's a special room called the start room, it's a special room called the destination room, and you're asked how many people, how many different badge numbers can go from start to destination. So what we're going to do is by the way, we are told that the number of rooms is 1,000 or up to 1,000. Number of doors is up to 5,000. Number of badges is up to 1 billion. So the number of badges is very high. The other numbers are manageable. And you're given a specific start room and a destination room. For each door, we know that it goes from a certain room to a certain other room, and there is a permit range, which we're just going to call min and max for that door. Okay? That's what you're given. So the main idea is to model this problem as a graph problem. And the first problem that we solved was, if I gave you a specific badge number, can you tell me whether this person can get from source to destination? We modeled this as a simple breadth first search. It also works with depth first search, because you can start from the source, you can figure out all the neighbors that person can get to, all the neighbors of the neighbors that person can get to, and eventually you ask the question, can this person reach the destination? So that's a simple breadth first search. You can also do this with depth first search. If your depth first search starting from source ever gets to the destination, then you know you can get there. Now, that's simply to check whether a certain badge number can get there. It doesn't tell you about ranges and counts and so on. So now we have to take this idea and put it into something bigger. So we need a second idea, and the second idea is that if we try every possible badge, we'll go nuts because there are 1 billion different badge numbers. But if we take our set of minimum and maximum values for each door, and if we sort them, now suddenly the number of different ranges becomes smaller, and for each of the ranges we know that they are able to go through exactly the same doors. There is no point in repeating it for 49 and 50 if they are part of the same range. So we reduce it to the problem of identifying the ranges. Sorry, I shouldn't call it ranges because the ranges is what you use for the door. These are intervals in the range 0 through 1 billion. Badges can be any number between 0 and 1 billion, but you can break that into smaller intervals where within each interval these people can go through the exact same doors. So there's no point in doing the computation over and over again for every person in the same interval. So we break it down into at most 2m minus 1 intervals after sorting, and then run the previous test asking can they get from source to destination. And then once they are done, we can, there's a little extra that you have to do where you have to add up the size of the interval to figure out how many badges can get through from source to destination. And then that's what you report. So here is the algorithm. The algorithm says, first of all, take all the minimum minimum and maximum values for each range, for each door, sort them. That will give you the numbers B1, B2, B3, B4 up to 2m. You take one of those intervals, that means from bi to bi plus 1. Pick a middle number, doesn't matter which one, and check whether that person with that badge is able to get from source to destination. That's a simple breadth first search job for you. Then if if that person was permitted, then you keep track of that range, because those are the number of people that can get through for that particular interval. And then you add up all the lengths at the end of the ones that are permitted, and you're done. I think I made a mistake here. This should be CI, not CI minus 1. I don't know why it says CI minus 1. Okay?
So just to make sure, that the thing that you're sorting are those ranges of the door?
These are all, you're taking all the minimum and maximum values.
Yeah.
You don't care which door it belongs to. Put it all into one pot and sort it. Okay? But did that make sense?
Yeah.
So if there are 5,000 doors in this building, and each one has some crazy range, they're all going to show up here somewhere. And I only have to pick those values. So let's say one of them is between 23 and 27. The other is between 2 million and 3 million. All those numbers are there in here. I don't care what happens between those values, because they all look identical. All the guys between this and this value, regardless of whether this is a minimum or a maximum, doesn't matter. They will be able to go through exactly the same doors. And that's the key. So that means I don't have to try each one of these. And because this is a billion, this could each be a million, right? And so there's no point in checking a million people when you know that you're going to get the same answer. So that's the trick. And the time complexity turns out to be m log m for sorting, and then n plus m times m for the different values that you have to do a breadth first search for. The worst case is m squared. Because m is only 5,000, the whole thing is great. So we never look at each of the badge numbers, and that's important, because otherwise you're in trouble. Well, you could look at 10 to the 9, it's possible, but for each one you have to do a lot of work, and that's going to be a problem. And that's it. Shall we stop here?
Yeah, that's good.
Okay.